Good morning. Let's discuss AdaBoost classifier today. Our objective is twofold actually. First of all, we want to understand the details of this classifier. Secondly, we also want to understand this idea of how to read a pseudocode. Now, when we want to learn different algorithms in machine learning, it is easy to understand these algorithms from a higher level. But when we ask more and more questions about that algorithm, we may have to go into the pseudocode. For example, when we try to learn AdaBoost classifier, you might have seen pictures like this. This shows that we got a data sets with positive and negative labels, and we are building a decision tree with one split. It is called stumps. That means the level is equal to 1. So here the tree divided the data into two parts. Looking at the result, we can see that these positive values are actually wrongly classified values. Now, in the next step, we will increase the weights of those observations and we will build the next tree. Then again, we will look at the wrongly classified observations. So that is these three negatives. Then again, we will increase the weights of those observations, so on and so forth. So here we are showing just three trees. And then finally, we will bring the result of all these three trees together to get an overall prediction, which you can see that it is quite accurate. Very good. So we understood how AdaBoost classifier work from a higher level. But you may have questions about what is the meaning of increasing the weights, or how much is the increase in weight, so on and so forth. And finally, how are we going to aggregate the result of different trees, things like that. So such questions can be addressed only by looking at a pseudocode. So the second objective of this exercise is, let us go through a pseudocode and understand how to read it. And then finally, we will implement that pseudocode in Python. So we will code in the Python and get the result of a prediction problem using AdaBoost classifier. So before we go more into the details of AdaBoost classifier, let's place this particular algorithm from the point of view of a predictive algorithm. So broadly, it falls into something called ensampling. Ensampling means we are bringing together the results of many models to get an overall prediction. So how do we achieve this? We may build different models and bring the results together, or we may build same model, means algorithm is same, but we will use different data sets and then bring the results together. So we may use any of these two approaches to implement this ensampling process. But what is common is that finally we will bring the results of all these models together to get an overall prediction, which we expect that accuracy would be higher without, of course, overfitting. We will be always careful about not to overfit, is it not? All right, so let's go into the details of what are the methods of ensampling. Broadly, there are three methods: bagging, boosting, and stacking. In bagging, what we are doing is we will build homogeneous weak learners. That means we will use same algorithm to build the models. So that could be logistic regression or decision trees or naive Bayes or things like that. Algorithm is same. But different models are built by inputting different data sets. That means we'll make some changes in the data sets and will provide us inputs. Then we will build the results of all these models together to get an overall prediction. Now, when it comes to boosting, now one thing we need to keep in mind is that in bagging, these models are in parallel. That means one model would not have any implication on the next model we are building. They don't communicate to each other at all. While in boosting, again, the learners are homogeneous. That means we will stick with the one algorithm. That could be a weak learner like logistic regression or decision tree, etc. But the critical difference is that we will build these models one after another. So we'll build one model, look at the result, and make some modification in the data. Then we will build the next model, look at the result, make some modification in the data, so on and so forth. Ultimately, again, we'll combine the result of all these models to get an overall prediction. Now, when it comes to stacking, we will use heterogeneous weak learners. That means one model may belong to decision tree, second model may belong to support vector machines, third model may belong to logistic regression, so on and so forth. And these models are built in parallel. And then we'll combine the result of all these three models to get an overall prediction. So these are the broad three approaches. Of course, the AdaBoost we are going to discuss right now is an algorithm belonging to the boosting class. That means we'll build weak learners in sequence. Okay, now what we'll do is let's go through the pseudocode of AdaBoost classifier. When you look at this pseudocode, it may be little confusing because a lot of Greek symbols are being used and so many notations. Don't worry, once we go through these steps line by line, it should become more clear to you, and hopefully it would help you to read the pseudocode of another algorithm and understand what is going behind the scene. Let's take the first two lines. It says that given x1, y1 to xm, ym, it is referring to our data. So x refers to the features, y refers to the labels. So obviously we got m observations. M is the number of observations. Here x, that is our features, can belong to a real number. It can take a positive or negative value, any value. Yi, our label, can take only two values, -1 or 1, +1. Right now we are considering only a binary situation. If it is not binary, it can take other values. Now we are initializing d1 with a value 1 by m. Uh, as we just discussed, m is the number of observations. So 1 by the number of observations would be the value of d1, and that we will attach to all the observations. So that's why we are saying d1 of I. I refers to each observation. So first observation will have a value 1 by 1, second would have a value of 1 by 1, 1 by m, so on and so forth. It will be same for all observations. So that is what we are saying for I equals 1 to m. So across all the observations, this value of d1 is same, 1 by 1, 1 by m. And this is actually our initial weight. Remember, we were talking about changing the weight of observations, no? So right now we are starting with a uniform weight for all observations, and that would be 1 by m. Next, what we are doing is we are starting a for loop. This is required because we will be building many trees, so it is done under a loop. So t can take a value 1 to t. So if you are building 10 trees, capital T is 10. So small t will take a value 1 for the first tree. It will take a value 2 for the second tree, so on and so forth. So these trees are referred as weak learners. Okay, and the result of building each tree is a model, isn't it? So it is given a notation ht. So h1 is the first tree, h2 is the second tree, so on and so forth. And in machine learning, these models are addressed as hypotheses. So don't get confused. The statistics models versus machine learning hypothesis. So here it is the same thing. So hypothesis is actually model. So we will get these models ht, where t vary from 1 to capital T. Then what we are doing is, for each model or each tree, we are calculating these parameters. So let's assume that we have just built the first tree. Then the first thing we calculate is epsilon t, which is nothing but a parameter called total error. Now this total error is nothing but the proportion of observations where our prediction has gone wrong. So ht of xi is the prediction of our model. So h1 of xi is the prediction of our first model for each observation. Now we are saying that prediction is not equal to yi. That means it is a case of inaccurate prediction. So prediction is not same as what is actual. And then we are looking at the proportion of such observations. That is the total error. So if 10% of observations are having inaccurate prediction, that proportion is nothing but 0.1. That's the idea. Now, how do we get this proportion? So all we need to do is just sum up the weights of those rows where our prediction is not accurate. So initially we got 1 by m as the weight. So all we need to do is to sum up those observations where we have gone wrong. Now what we are going to do is calculate something called alpha t. Alpha t is amount of say or the importance of a model. So which is nothing but 0.5 into log of 1 minus total error divided by total error. So you can see that when the error is large, alpha t will be small, and when the error is small, alpha t will be large. So that is intuitive. So in situations where the error of a model is small, that model should get higher weightage. That is all we are saying. Then what we are going to do is, for each observation, that is I equals 1 to m, we are updating the weights. So the new weight is old weight multiplied by this term, where this term contains amount of say and multiplication of our actual label multiplied by the prediction. Now an interesting thing happens when our prediction is correct. This multiplication yi into hi will be 1. Why? Because when our prediction is correct, yi will be equal to 1, and h of xi, the prediction of our model, also will be 1, or vice versa. Ya equals minus 1 and our prediction is also minus 1. So when you multiply it, it will be 1. And exponential, that will then, if our prediction is correct, it will become exponential of minus alpha. Okay. And if our prediction is wrong, this term will be 0 and exponential of 0 will be 1. And we will have a weight here. Alright. So when we have, that means the way this equation works is that our new weight will be smaller when our prediction is correct. That is exponential of minus alpha. And our new weight will be larger when our prediction is wrong. That means it will become exponential of 0, which is 1, and we will get that original weight back. Alright, so that is how this equation works. Or in other words, we are increasing the weights of those observations when our prediction is wrong. Okay, and zt is a normalization factor we are using so that all these new weights will add up to 1. That is a basic requirement. Finally, we are out of the for loop, and we got the results of all our models, the amount of say we have, and the prediction we have. Now what we are going to do is just multiply the prediction with the amount of say and add up for each observations. Okay, so this is done for each observation and for each tree. So then what we'll get is that inside this bracket we can get a value negative or positive. Now what this sign function does is, if our value is positive number, it will make it 1. If our value is a negative number, we'll make it minus 1. And if it is 0, we'll keep it as a 0. So that is the overall prediction of our model, which is nothing but a combination of the results of each of our models. So that is what is happening inside this equation. So we are summing it up across all the models. Alright, now what we are going to do is we will open our Anaconda notebook, and we'll go through that notebook and understand how to implement this pseudocode in practice. This notebook you can access. I will provide you uh, under the video, under the resource section. I will give you the link to this notebook. All right, let's open the notebook. Okay, let's go through it one by one. We are importing all the required libraries. Right now we are using a data set that is available as part of sklearn. This is a data set about breast cancer. Right now we got the label 0 and 1, which we are converting it into -1 and 1. Now let's take a look at the distribution of our label. Plus 1 is the 357 and -1 is 212. So it is somewhat a balanced data set. So these are the kind of variables it got: mean radians, mean texture, perimeter, area. So it is some information about the tumor that patient got. And finally we know whether it is a cancerous tumor or a benign tumor. So 1 and -1 would indicate that. Columns gives us the names of the features: mean radians, mean texture, so on and so forth. In step 1, like we have just discussed, we are essentially reading the data and creating or initialize D1, our weight, initial weight, which is nothing but 1 by m. In our case, m is 569, so we got 569 observations. And D1 we initialize as 1 by m. So let's take a look at that. And we are reading D1 as part of our data set. So in our data set now we have an additional feature. It's not exactly a feature. Additional column D1, and the value is this. Then what we are doing is we will start the for loop and then go through the step. So right now we are not going through this for loop to understand the process. Then we will implement the loop. So let's build a weak learner. The weak learner is decision tree classifier with depth equals 1. So it is nothing but a decision stump, one split. And this is the result. And you can see the stump it has created. Once a model is or a tree is built, now we need to calculate all those requirements, starting with the total error. So we'll calculate the total error, and then we'll calculate the amount of say, and then we will update the weights. So let's do that. Ypred is the predicted value of our tree, and let's read that predicted value also into our data set as Ypred1 because it is a first tree. Now total error is calculated as sum of the weights of all observations where our prediction is not correct. Okay, so that is total error. Then we will use this total error to calculate amount of say, that is alpha. And we know the equation of that, 0.5 into log of 1 minus total error by total error. And we are reading that alpha also as alpha 1 into our data set. Next process is we are updating the weights. So the new weight is D2. which is equal to old weight into exponential of the equation we have just discussed. Our actual y multiplied by the predicted y. And zt is the sum of all the weights, and the new weight is the new weight multiplied by the normalization term. So we got the new weight, and we are adding that weight also into our data set. So let's take a look at that. So this is our data set, this is our actual y, this was our old weight. So then we got a predicted value, and this is the amount of say, and our new weight is something like this. So if you look at the D1 and D2, you can see that the new weight is somewhat smaller than the previous weight. Why? Because these observations are correct prediction. You can see here y is 1, y pred is 1, y is minus 1, y pred is minus 1. So these are observations with correct prediction, and the new weight is smaller than the previous weight. Now let's take a look at a few observations where the prediction is wrong. So you can see here y is minus 1 and the predicted value is 1. Now the original weight was here and the new weight is here, and you can see that the weight is now increased for these observations, and the reason is that these are the observations where our prediction is not correct. So this is how the AdaBoost classifier work. Here we are doing a small exercise to understand, a synthetic exercise to understand the connection between total error and amount of say. You can see that when the error is very small, amount of say is very high, and when the error is very large, the amount of say is very small. Actually it is negative. That is the connection between amount of say and total error. Now what we can do is, let's implement the entire algorithm by bringing in the loop. Previously we discussed without loops, so that process is clear to us without using all those notations. So here again we are reading the data set again. We calculate the initial value of weights as 1 by 1 by m, and now we are starting the for loop, and within the for loop we are going through building the model, getting the predicted value and calculating the total error, then amount of say, and afterwards we are updating the weights as D2. Then what we'll do is we will drop the original weight and we'll rename the new weight as D1, so that when the loop repeats, it will use the D1 weight, and will continue the process. So every time the for loop returns, the weights are getting automatically adjusted through these steps. And you can see here our data set now would contain actual y and the weight, then predicted value of our first model, alpha of our first model, predicted value of the second model, alpha of our second model, so on and so forth. So data set now contains predicted values of each models and the alpha values of those models. Next, what do we require to do? Sum it up. And the logic of summing up we have just discussed. We'll multiply the predicted value of each of our models with the amount of say and add up. So that is what we are doing here. We have initialized our overall predicted value, and then we'll multiply our alpha values with the predicted values for each of our models, and we'll add up. Then we will use nb.sign to get the overall predicted values. So all the negative values it will convert to -1, all the positive values will convert to 1. Afterwards, now in our data set we got the overall predicted value right here. So now what do? We'll quickly take a look at the quality of our model. So we will calculate the accuracy score, and before that we'll create the confusion matrix between y and y prime. So our model got an overall accuracy of 0.92. Keep in mind that we built only 4 trees or 4 models. So if we increase the number of trees, our accuracy may increase. But anyway, we didn't attempt that because that was not our objective. So go through this notebook in comparison with the pseudocode, so that we can understand how pseudocode comes to life. So hopefully this will help you to read through pseudocode of another algorithm. Anyway, I will follow up this exercise by choosing pseudocode for AdaBoost regressor and how do we implement that. Then other algorithms would follow. My only request is to give some comments under the video so that I can improve the next exercise. Thank you very much.